This is the seventh session on signals and systems, and we are going to study a function which will generate signals which can be expressed in terms of piecewise linear segments. And we will also see how to write the main program which will call this function and generate the signals. That is what we are going to do. In my previous video, actually we had discussed this program, but later on I found there was an error in it. So I have removed it from the previous video, this particular part. And in this session, we'll discuss the corrected version. Okay, so let us start. So discrete piecewise linear function. What is the input to this? Input to this piecewise linear function is end points of all the lines. So we are assuming that our signal is capable of being represented by a number of piecewise linear segments. So every line, every straight line, if its 2 points are known, the others can be calculated. So our main program will provide these endpoints for the lines, and the function will calculate all the intermediate points and then give the complete signal. That is what it will do. So as we said, input is going to be endpoints for all the lines. And this data is used by the function to calculate all the intermediate points. We know that if 2 points on the straight line are known, then we can calculate its slope, we can calculate its intercept, and therefore the value of the sample at any other point on the line can be calculated. So to illustrate this, let us take an example input data. So this is the sample index n. So it starts from -3, and note that for the first line the endpoints are -3 is the index, 0 is the sample value. The next point on the line is -1, next endpoint, and at this point the sample value is 1. Note that the intermediate values will be provided by the function itself. For example, we know that for discrete signals, the n will actually change with a unit value for every new value. That is, from -3 it will go to -2, then it will go to -1, then it will go to 0, and so on. But the input signal that we are providing provides only the endpoints for the lines. So this is the first line. For the second line, these are the endpoints. When this is -1, there is 1. When this is 0, there is 0. So this is for the second line. Then for the third line, n equal to 0, x equal to 0. When n is equal to 3, x is also equal to 3. Finally, when n is equal to 6, again note that the intermediate values here are not given. They will be calculated by the function. So for the last line, for n equal to 3, x is equal to 3. And for n equal to 6, this is equal to 0. In fact, this is also shown pictorially here in a graphical fashion. So these points are given. So this is one straight line, this is the second straight line. So how do we distinguish between the segments? When the slope changes. So that is why this is one segment, this is second, third, and fourth. And as you can imagine, the number of segments that you will have, or the number of straight lines that you will have, will be one less than the number of points which are given, for the obvious reasons, because the first 2 points will generate one line. Thereafter every new point will generate one more line. So for the first one you require 2, and then you require just one more point for the subsequent lines. So 1, 2, 3, 4. So if you had 6 points, it will generate 5 linear segments, and so on. All right. So when we write the function, what that function will do, it will generate all intermediate points. So ny is the sample index for the complete signal which is generated from the function. So here it is from -3 to -1. So one intermediate point is -2, which is provided by the function. Similarly for others. Here, of course, from -1 to 0, you don't need any insertion, because this is away only by a unit value. Then between 0 and 3, of course, you require insertions. So 1, 2, and so on. So you will require insertions for the sample index values, and you will also require the insertions for the sample values themselves. For example, in this case, the endpoints were -3, 0, -1, 1. So the intermediate point, that is -2 and 0.5, that will be inserted by the function itself. All right. So of course from -1 to 0 there is no insertion required. But if you see from 0 to 3, then 1, 0 to 3. So you will require 1, 2 inserted, and these values also inserted, 1, 2 and 3. Note that 0 and 3 values are given. So 1 and 2 are inserted here. Similarly for others. Okay. So I hope it is clear what is the nature of the input signal and what is the nature of the output. So idea is to reduce the labor. That is, see, it is always possible for us to write this entire signal manually. If that is provided, then of course you don't need any function. But if you got large number of sample points and the endpoints are comparatively low, then it is certainly quite useful to use the function. So in many cases in signals and systems, if you do not require large sample points, then you can always do it manually. Simply define your n completely, define your x completely, then you can always plot the signal, you can always process the signal and so on. But if the number of points are large, then it makes sense to write the function and then use it. Okay. So let us now see the function itself. Again, for explanation, we are assuming that this is our input, and actually this is the output which the function will generate. And for the sake of explanation, I have showed the output before I am showing the function, for the sake of explanation, because this tells you what the function is doing. For example, this -3, 0, -1, 1, these are the two endpoints for the straight line, and this is inserted by the function. Here you don't need any insertion. One important thing you should note is that when this sequence is generated for the first segment, this particular point is going to be common between the first segment and the second segment. So if you generate the second segment also identically, this will be an additional point. So we'll have to take care of that, and we will see how to do that when we study the function program. All right. So let us start. So function nyy, these are the output variables. So this is the output sample index, and this is the output sample value. These are arrays, of course. And then we say piecewise, linear, discrete. I have written 3 only because while I was developing this function, I went to 1 or 2 iterations, so ended with 3. It doesn't matter, whatever you call it. Then the input arrays are n and x. These are the input arrays which are written here. All right. So what is the first thing you do? You find the length of n. Okay. So in this particular case, that means it will give you the number of samples, number of sample values for n. So in this case, it's going to be 1, 2, 3, 4, 5. So nt, after you execute this statement, will hold the value which is 5. Then what you do, you initialize the output arrays. So output sample index values and output the sample values themselves, both are initialized to null, and we'll go on concatenating in the iteration that we shall study next. So what do you do? For I equal to 1 to nt minus 1. Why nt minus 1? Because remember, we have said that if we have 5 values here, then you will get 4 segments or 4 straight lines. And you want to generate the equations for 4 straight lines differently and then concatenate all the points. That is what you want to do. That is why this is nt minus 1. Then what do you do? Remember, these are the 2 points on the straight line, and we want to calculate the slope and the intercept. So we calculate it like this: x1 is equal to xi. So initially when I is equal to 1, x1 will be equal to x1 itself, n1 will be equal to n1. Similarly n2, that will be ni plus 1, so n2, x2 also. Then we calculate the slope. All of us know how to calculate the slope. So that is x2 minus x1, difference of sample values divided by the difference of the uh, sample index. That is usual way of calculating the slope. Then you can calculate the intercept also in this particular fashion. Then what you do, then for the first segment, you generate the entire sample index array, entire sample index array for the first segment. So it goes from n1 to n2 with an increment of 1. So remember, n1 was calculated from here, n2 was calculated from here. So n1 is known, n2 is known, and the increment is 1 because for discrete signal this is always going to be 1. Then you calculate y1 once ny, understand this is an array. So when I do this calculation, I get my entire array, and that is the equation for this line. Okay. So I get all the points now, all the intermediate points are obtained for the first segment. And now what I can do, I can concatenate. So ny was the initial value which held a null. So now that is concatenated with ny1. So I'll first get ny1. Then y also similarly, y and y1. So y was null here. So now it is y1. Next time I go through the loop, what is going to happen? This I will be 2, and this is of course nt minus 1. So this is going to be 4. Now this is 2. So when you evaluate the next segment, understand that the first point, the last point of the previous segment is going to be the first point of this segment. So that is going to be repeated. So when you do this iteration for the first time, you don't have to worry. You got 2 points, 2 distinct points, and you calculate these arrays. But after this, for example, when you go from -1 to 0, and for these sample values are 1 and 0, here what is happening, this particular point was calculated by the previous iteration. So in the current iteration, you use these values to generate the next set of values, but you start from the next one itself. So that exception is handled here. The following if statement is to avoid duplicates. So if I is greater than 1, note first time you don't have to do it, but as soon as I is greater than 1, you have to take care of this. So your ny1 starts from the second value itself and not from the first value, because otherwise it will call duplication. So that you do for ny1, that is for the sample index, and you do it also for the sample values. Okay. And then this ends. So when you go through all the loops, second time this is done, sample values and index for the second segment is calculated, third is calculated, and the fourth also calculated. All right. So I hope this is clear. Incidentally note that this end was for if I greater than 1, this ends, and this end is the end for the function itself. Okay. Let us now look at the main program. So clear console as usual, clear the variables, clear the figures. Now you define your n and x. These are the endpoints of the various segments. And now you call the function. All you have to do is ny, these are the output arrays. So pld3, these are the input that is supplied from here. And just to check, you can display also ny and y and verify that you are getting correct values there. And then of course you can plot the stem plot ny, y, and all these usual things like line width, grid on, x label, etc. But at the end I have also done hold on and plotted this. This is plotted not because it is required, but just for our understanding. Because for a discrete plot, just the vertical lines, so the line plots are good enough. But in order to see how the straight line, what is the slope of the straight line visually, we are plotting that also. So the plot will give me a continuous graph. Okay. So when you execute this program, this is what you will get. This is what we have been discussing. This is the output that we wanted, and now you can see all the intermediate values are filled. Although this is -3, -1, so -2 is filled here. -1, 0 is okay. Then from 0 to 3, so 1, 2 are filled and the 3 is available. Then from 3 to 6, so 4, 5, these are filled. So not only the sample index values are filled, but the sample values themselves are also filled. So you can see this is filled, this is filled, this is filled, and these values are also filled. And these are of course the endpoints which are supplied by the input. So I hope it is now understood how to generate a piecewise linear signal by using a piecewise linear function. Of course, note that this is useful only when you have large number of points. Otherwise, you can always manually just provide the entire array for n and the entire array for x, and then process them, plot them, whatever you want to do. And that's all in this session.